Hello, welcome back to the second lecture given by Professor Vishwanath. He's going to talk about from band-aware fermions to band topology. Just a reminder, the lecture given by this afternoon, still the order is reversed compared to the original schedule. So Professor Xiaodong Xu is going to present the first one in the afternoon. Then again, Professor Vishwanath. Yeah.
Okay, so is this on? Yeah. Yeah, so thank you for organizing this very nice school. So I'm hoping to learn things from the other speakers and from everyone in the audience during this couple of days that I'm here. So I'll be giving 3 lectures, and I want to end, in the third lecture, talking about this very new and interesting problem, this system called twisted bilayer graphene. And to keep things, there are many different aspects, and of course it's a very active research topic. But what I'll try to focus on is some unusual aspects of the electronic structure of this system. But to get there, I'll need to build up some background, which is what this first lecture will be about, and let's see how far we go. Okay, and it depends a little bit on people's background. So we all know that graphene has these Dirac points, right? In the electronic structure of graphene, you have Dirac points. So the way I'll try to think about band topology, or the topology of non-interacting fermions, is to sort of use this Dirac equation, or the Weyl equation, as a building block to access these topological phases and to understand the topology of non-interacting fermions. Okay, so in some theoretical sense, this is relatively straightforward because we're going to be talking about non-interacting particles, but there's a lot that's known about it, and it strongly informs questions about interaction physics as well. Okay, so this is things that we have a lot to say about, and I'd like to make sure that everyone working in this field or in related fields is sort of aware of these basic things. Okay, so some of you may find this slow going in the beginning, but hopefully there'll be something in the lecture that you didn't know, and the students can feel free to sort of interrupt me with questions, but hopefully at the same level as the lecture. Okay, we'll sort of go into more advanced topics a little later, but we'll kind of start simple. In fact, I want to start talking about quantum mechanics. Okay, so really 0 plus 1 dimension, and just to make sure we're all on the same page about some few kind of elementary facts about the geometry, if you like. Okay, so really the geometry of quantum mechanics, and some simple questions or simple notions about quantum systems that will kind of appear in disguise when we talk about higher dimensional band structures. Okay, so so let me begin over there. I guess there's no point sliding these boards, right? There's nothing behind it. There's another board here. Nope.
Just a screen back there. If you want to show some slides, you move them aside.
Yeah, right. Okay. So I'll have to work with this real estate. I think I would have written smaller if I had known. Okay, so just to begin with the simplest possible system you could imagine. So let's say you had a 2-level system. Okay, so the Hamiltonian is just some 2 by 2 matrix. And up to some irrelevant overall energy shift, you can simply write it as a bunch of Pauli matrices. Okay, so Okay, and you get energy levels, of course, that are simply the norm of this vector. Okay, so imagine that you wanted to tune the degeneracy of these two levels. So you have a pair of levels. Okay, that's the splitting. And imagine that you wanted to tune parameters in order to get degeneracy. So typically a Hamiltonian would have no degeneracy. And you want to get to a position where both of these energy levels are degenerate. Then, of course, what you need to do is you need to tune Okay, so that simple fact actually underlies a lot of the topological phenomena that we're going to discuss. This will ultimately be related to both the Weyl fermions okay, so if the three parameters are the three crystal momenta, then a pair of states in the band can be brought into degeneracy. And that's why you get these Weyl points in 3+1 dimensions. We'll also see it's related to the Chern number. Okay, so the sphere that surrounds, the sphere in parameter space that surrounds one of these degeneracy points will be associated with a Chern number. That will be an invariant that we'll see is, of course, very important in thinking about 2+1 dimensional band insulators. Okay, now of course, if you had some symmetries, you may not need to tune all three parameters. For example, if you had time reversal symmetry, and let's implement it in the usual way, which is just implemented as a complex conjugation. Okay. So then, of course, you're not allowed all of these Pauli matrices. And the usual way of writing tau y is imaginary. So the ones that you are allowed are the x and z. So now you just have two parameters. Okay, and you can get a band degeneracy. You can get a degeneracy of these levels by just tuning two parameters. Yeah, or you can get a band touching if you like. If you have this symmetry, you could get this band touching in a two-dimensional system. And this is actually related to the Dirac points in graphene. Okay, so you have two parameters, kx and ky. You can tune them in order to get a degeneracy. Okay, so one thing that we're going to be a little careful about when we talk about time reversal and band structures. Typically, time reversal will reverse the crystal momentum. So actually, the symmetry we're going to talk about there is a combination of parity of reversing all the coordinates and time reversal. So this will be some new kind of time reversal T prime, and that will play the role of this complex conjugation over here that simply reduces this Hamiltonian down to two parameters. Okay, so again, there is a simple counting argument where you end up with this, where it's related to the physics of a band structure. And finally, you can think of a different kind of time reversal, which is, here, let's call it time reversal theta. Actually, can people see down there? Or?
It's a little too low, yeah.
Okay, so the time reversal we're actually used to for electrons, which is you do complex conjugation, but you also exchange the spin up and spin down. So if you had electronic wave function with two components, okay, so this time reversal would take C up to C down star and C down to, okay, so that's this theta. Okay, so this the thing that's special about this kind of time reversal is that if you square it, of course, if you reverse time twice, it's the identity operation, except you end up with a minus sign on every fermion. And so it turns out this minus sign is not removable because of this complex conjugation. Okay, so time reversal, the way it's implemented, unlike any other symmetry, it's actually an anti-unitary operator.
It's a question.
Yeah.
Is it Hamiltonian there tau z or tau y? A2.
It's Z. Is it, you can't tell the way I've written it, or? So in the usual notation for Pauli's, this is the imaginary matrix. Right. Of course, that's just a notation, but let me just use that notation. Okay, so, so unlike usual symmetries, which are implemented with unitary operators, okay, think of spin rotation or any spatial symmetry. Okay, so you have some matrix U, you act on some state, and if I were to give you a linear combination of two states, you can take that unitary operator inside this linear combination. Okay, just a linear operator, but of course with time reversal symmetry that's not true because there's complex conjugation involved. If time reversal is acting on something like that linear combination, okay, you have these you have these complex conjugation of the coefficients involved. So obviously it's not a linear operator. Okay, it's an anti-linear operator. It's something we're not very used to, and it can lead to non-trivial effects. And one of the non-trivial effects is that this time reversal can square to -1, okay, when acting on these one particle wave functions. And if this was a unitary operator that's squared to -1, you can just absorb that in the definition of the unitary. Okay, but you can show that for an anti-unitary operator, regardless of what phase change you make over here, in order to try and get rid of that minus sign, you can show that this minus sign is robust. Okay, and that's a nice thing to prove. Okay, so we know that this is the origin of the Kramer's degeneracy. If you want to implement a symmetry where this anti-unitary symmetry squares to -1, you cannot do that with a non-degenerate state. You need at least a pair of states, up and down, that you can send into one another like this. And that ends up giving you this twofold Kramer's degeneracy. Okay, so okay, and so in other words, if I were to take this implementation of time reversal and demand that this Hamiltonian is invariant, okay, so if I demand that theta h, okay, so that is just a symmetry acting on the Hamiltonian and leaving it invariant, you can show that none of these coefficients are allowed. All of them violate time reversal symmetry, okay, with this implementation of time reversal. Okay, and that of course means the two levels are always degenerate. That's just the Kramer's degeneracy. Okay, so you can just think of these towers as spin matrices, and of course under time reversal, the spin is reversed. Okay, so for this case, you can actually think about a slightly more complicated problem, which is, let's say you have a Cramer's degenerate state, and then you have another pair, and you can ask, can I bring two sets of pairs into coincidence? Okay, you can think about a 4x4 Hamiltonian, and you can try to figure out in how many parameters you need to tune in order for that to happen. Okay, let me leave that as an exercise. Okay, how many parameters do you need to tune to bring two of these Cramer's pairs together? Okay, and it turns out so the answer is related to the so-called four-dimensional quantum Hall effect. Okay, just like in this case, without any symmetry, tuning three parameters is related to the two-dimensional regular quantum Hall effect. Okay, so that's some basics about this problem of I guess it's probably due to von Neumann, how many parameters you need to tune in order to get things into coincidence. But what people realize later is that it's also related to things like the Berry's phase. Okay, so let's talk a little bit about the Berry's phase. Okay, so we're going to start, again, let's think about this two-level system. We can generalize it later. You imagine that you have some Hamiltonian like that, and you imagine that that Hamiltonian, which is parameterized by this vector, is a function of some parameter, let's say time. Yeah, but it changes in time in such a way that the gap is always open. So this the modulus of this vector is always not equal to 0. And you do it in a way that is slow, okay, slow compared to the gap. Okay, so you have this kind of adiabatic evolution. You stay in the ground state, or you more or less stay in the ground state, and you think about a circuit where you start at 0 time and you end at some time t, and you return to the same point. Let's say you start at A0 and you return to A0 in this adiabatic process. And since this gap has always remained open, you're guaranteed to return to the same state. So you start in psi naught, you end up with the same state psi naught, but with some phase. And as you all know, this phase has two pieces to it. One depends on the time. It's a dynamical phase. The fact that you have some energy splitting, and that energy splitting varies, and you integrate that with respect to time, that gives you this dynamical phase. It depends on the precise way in which you got from here to there, all the details. But there's another one which only depends on the path. It's independent of how fast you go around, as long as you remain adiabatic. And that's the Berry's phase. Okay, so let me remind you about this Berry's phase. I know most of you know about this, but let me sort of cast it in a way that will be relevant for the topology of band structures. Okay, so we are thinking about this two-level system controlled by this vector, right? So you have this vector sweeping out some something on the sphere. and the state follows that vector, and we want to know what the Berry's phase is associated with this particular path, right? Okay, for this particular curve C. Okay, so now it turns out it's actually somewhat, a little bit involved to calculate the Berry's phase. But what is easy to do is to calculate the difference in Berry's phase for two very close by paths. Okay, and the reason it's actually hard to calculate the Berry's phase is that when you write a phase, you want an expression for this gamma c. So this gamma c is intrinsically ambiguous. Okay, the thing that really is physical is the exponential of this e to the I gamma c. Okay, that's the thing that will appear when you do this process. That's the physical thing. Okay, so gamma c itself, although we want an expression for gamma c, it's only defined modulo 2 pi, and any expression I write down should have that inbuilt ambiguity. Okay, you cannot really pin it down to anything more than two, integers multiplied by 2 pi. Okay, so but if I think about two paths that are very close to one another, and I think about the difference in the Berry's phase between them, that is easier to calculate. That's just you can think about small differences, so you don't suddenly acquire a phase of 2 pi, right? So let me think of one path like this, and another path that is pretty much the same, it only deviates a little bit, and let me call this new path a of t plus delta. Yeah, and so you can do a small computation. I'll leave that as an exercise. It'll be in my notes. But you can show that the difference in these two Berry's phases okay, so let me go with the difference delta gamma. Okay, so you can show that this is just okay, so it's a triple product. So we're thinking about this vector A. The vector A has some velocity, dA by dt. It's tangent to the surface. And then you have delta A, which is again tangent to the surface. You take the cross product, that's orthogonal to the surface, take the inner product with A. This triple product is just telling you the area, if you like. So if you have these two paths, okay, so let's say this path is A plus delta A, and this one here is A.
Restricted
Yeah.
A to unit vectors at this point?
Good point. Yeah, this is unit vectors. Sorry, I should have said that. Yes, so actually, let me spend a minute on this. So this spectrum that we had, we said that the energies are plus or minus mod A. Okay, and but for all of our purposes, it'll be useful to think about a different, slightly different problem where the difference in the energies is just plus and minus 1. Okay, so you just imagine normalizing your Hamiltonian. You had a Hamiltonian, just normalize it by the magnitude A, or the modulus of H, if you like. And this has a spectrum. This is what we might call the flattened Hamiltonian. And what will appear there, instead of the vector A, it will simply be the unit vector that appears. And it's really these unit vectors that I'm thinking about. Okay, and the norm of this thing also, I want to flatten this Hamiltonian so that this delta A, the lowest order, is just orthogonal to A. Okay, so I also want this. Yeah.
Is the unit consistent with the, because we have time derivative and this side we have like angular.
Yeah, so good. So I want to integrate this. So this is for a little patch over here. And then I integrate this over time to get the entire Berry's phase.
Sorry.
Yeah.
What's the physical meaning of delta A again? The
Of
delta A.
delta A?
Yeah.
So imagine you have two paths. So you have one path that looks like this, let's say. Then you have another path very close to it, looks like that. So I can look at the difference between these two paths. That is delta A. And what this expression tells you is the Berry's phase you would get going on this path minus the one you would get on going from the other path. And that is a small quantity because it only depends on this tiny difference. And it's easy to write down that quantity. So we'll see that there is a physical quantity that has very similar properties, which is the polarization. Let's do just a 1D system. Okay, so imagine you had some crystalline insulator. You can talk about the charge polarization. So you have electrons, and you have, of course, the neutralizing ions. So you have some electrons and ions. Okay, and you want to define a dipole moment for this thing, which is related to these tiny dipole moments. But there's an ambiguity over here, okay, because of the periodicity of this crystal. How do you associate the plus and minus charges? You could take a plus charge in one unit cell and associate it with a minus charge in the next unit cell. So there's some sort of ambiguity by adding units of polarization, E times A. You can add these units. So there's some intrinsic ambiguity in the polarization. So all you want to know is the polarization modulo such ambiguities. Okay, so very much like the Berry's phase, which is only defined modulo 2 pi. The polarization in such a system also has that ambiguity. And also, what it's easy to show is that it's much easier to calculate the change in polarization. You took a material and you changed some parameter, and you compare the polarizations after the small change. The change in polarization and what you simply do is you integrate the current that you get. Okay, so you know that the divergence of the polarization is the current, is the density, the charge density. So if I look at the time derivative of the density, which is related to the current by the continuity equation, what you find from that is that this time derivative of the polarization is just related to the current. Okay, so if you want to figure out how the polarization changed, all you need to do is to integrate the current over time. Okay, so delta P schematically is just the integral of J over this parameter lambda that you're using to change your system. So you imagine changing your, this physical parameter, measure the currents that flow in the process, and then you can figure out the change in polarization. Okay, so we're doing something very similar for Berry's phase. When you write down this expression, it's the difference. The actual calculation involves just figuring out the difference in phase, going from here to there versus going along that path. Okay, and then you add all such pieces, and you end up getting this. Okay, so let's use this, to find an expression for the overall Berry's phase. Okay, so if you interpret this expression physically, what it tells you is that the difference in the Bery's phase is just the area that's enclosed in the strip over here. Okay, so okay, so it's very natural to assume that the Bery's phase for any path is simply the area enclosed inside that curve. Okay, so okay, so you can write this in a slightly more sophisticated form, which we'll use simply as the connection. Okay, so you have some state A. You look at its overlap with the state at a slightly different time. These are all the pieces of the phase that you have to pick up. And then you want to integrate this, we call this A. And this gamma is just the integral of A around this path. Okay, and of course, we know by Stokes' theorem, you can write this as the integral over the surface, curl of A. Okay, and for this to be the area, you need that the magnetic field is just 1/2. So when you integrate this magnetic field over the entire sphere, okay, you have a total flux of exactly 2 pi. Okay, so you can relate this problem of Bery's phase once you know that it's simply the half the area enclosed to the problem of a unit magnetic monopole. Okay, so something that's spewing out field lines. Total flux of that monopole is 2 pi.
Excuse me?
Yeah.
What's the S means in the last equation?
This is just the surface area
Okay.
that's enclosed over here. Yeah, so yeah, this will be more precise in my notes. So I may have some factors off in this, in these equations. Okay, so okay, so let's go back to this ambiguity, which turns out to be important. So we said that there's this ambiguity when we define the Bery's phase. You can have this gamma being off by 2 pi, right? So how do you see that ambiguity? Because here it seems like you have a perfectly well-defined expression for the Bery's phase. Okay, but if you think about it, what is this area that you're talking about? So we're using some sort of right-hand rule and taking the area that's inside over here, and we're saying the Bery's phase is related to this area A.
Excuse me?
Yeah.
Where this 1/2 comes from? The half, gamma equals half of the area. Where does this half come from?
You can think of it as it's really a spin a half. But yeah, that's a good question actually, and it's sort of related to this this ambiguity. So let me talk a little more about it. Yeah. Okay, so so there's a different area that you could have picked if you wanted. So if you have a sphere, you have this area over here, and you also have the area outside. Okay, just 4 pi minus a. Okay, let me call it a2 or a prime. Okay, and a perfectly good definition of this Berry's phase is to pick the area outside this curve, right? So it should also be, there should be another way of defining it, where this is half times the area outside a prime. Okay, but using the same sort of right-hand rule, you'd put a minus sign over here. You're just moving around in the opposite sense. So this should be a perfectly good expression for the Berry's phase as well. And of course, this works out essentially because of this equality, right? So I can write this as 1/2 a. This was what we had before. Okay, the area a minus 2 pi. Okay, and of course, because this gamma is only defined in the exponential, you don't really care about this 2 pi. Okay, so so this goes back to this question of 1/2. This doesn't justify it, but it tells you that this is the smallest coefficient that you could have. Okay, so if you had let's say you had 1/4 over here, then this would not work out. Okay, so this sort of tells you that spin is quantized, and the unit of quantization is not integers, but these half integers. It's one way to think about it. Okay, so this is sometimes called the Berry flux, Berry curvature. And this is sometimes called the Berry connection. Okay, so another takeaway you can get from this is that the charge inside over here has to be quantized as well. We saw that the unit charge allows you to make sense of this ambiguity. If you had any other quantization of the magnetic monopole charge inside that sphere, you would run into problems. Okay, anything smaller, you would run into problems. Okay, so this fact, the fact that this magnetic monopole charge is quantized, will ultimately turn out to be the origin of quantized Chern numbers. Okay, so this is the physics of this Berry's phase. On the one hand, this Berry connection is directly related to the polarization. You'll see the analog of this Berry's phase is just the polarization. And the Berry curvature and the integral of the Berry curvature over the whole sphere being quantized is related to the Chern number. Okay, so all of this is simply there in quantum mechanics. It's a question of introducing momenta to give you the two parameters that move you around the sphere. Okay, so let me now talk a little bit again, moving up to the next simplest case, which is just the 1 plus 1D band insulators. Okay, so it looks like we're making very slow progress. 0 dimension, 1 dimension. When are we going to get to 3 dimensions, right? But it turns out that once you do this, and you're a little bit sophisticated about understanding how different dimensions connect together, you're pretty much done. Okay, so we'll see how we can go from here, what we learn over here. We'll sketch how you can classify topological phases in all dimensions of free fermions. Yeah.
Sorry, one clarification. The field of the field curl of A, that's the field of the magnetic monopole, right? It's not.
Yeah.
It's not 1/2. It's 1/2 times. Well, it should be 1/2 times.
You are right.
Over.
No, wait a second. So this is going to give you the 1/2, right?
Right, right. But there should be some unit vector divided by the norm square root. It should be. It's the field of the magnetic monopole, right?
Yes.
So it should be 1/2 times a vector, right? So.
Yes, so this
Yeah,
is
almost
ds
certain.
hat, so yeah.
Yeah. Okay. Thanks.
Yeah. Yeah, so yeah, I have this a little more clearly in the notes, hopefully. And it's sort of standard stuff, but I'll try to get all the factors right in the notes. Okay, so the plan then is to do this 1 + 1 dimensional case. And eventually what we want to come up with is a classification of topological phases in different dimensions. So just to give you a heads up of where we're going. Actually, how much time do I have?
Until so half an hour.
Half an hour. Okay. See how far I get. Okay, so I'm going to explain this table, but we have we're going to have 10 classes. And this will be a dimension. Give myself a little more space. Okay, so there'll be 2 of these so-called complex classes and 8 real classes, and I'll explain this in a second. And our aim will be to study their topological phases in different dimensions. Okay, and it turns out you only need to think about dimensions modulo 8 when you're classifying these phases. And even within that, there's a lot of interconnectedness between different classes and different dimensions. And what we'll do is we'll try to fill in the dimension 1 entries using this simple example. And once we do that, we'll be able to figure out topological phases in all dimensions, at least for these 2 classes. Okay? And then we'll talk about the real classes, which will work very similarly. I won't go into full details, but yeah, but this is just to let you know that this isn't some random collection of examples. It'll actually be the relevant ones to build that table. Okay, we'll also see why, what is the logic for only looking at certain symmetries and not others, and so on. It at least defines a problem that you can come up with a complete solution for. Okay, so I'll follow the lectures by Charlie Kane. I wrote these lectures and then I found he had some lectures extremely similar. Okay, so we're going to be talk about 1 + 1 dimension, and we'll talk about something known as the SSH chain. Sue Schrieffer-Heger. Pretty sure some of the spellings are wrong. But okay, so we have a chain with 2 sides. So it was originally cooked up to describe a material called polyacetylene. But we won't need that, so we'll just talk about this model which has 2 sides. Let's call them A and B. Let me shade the A sides. So it's a system with 2 sides per unit cell. And we'll have a hopping, let's say T1 between the A and B sides in that direction, and T2 in the other. We should write T2 below. Okay, a very simple model. Later we'll introduce an on-site potential, which will be different between the A and B sides, but let's just stick with this for a moment. So we have Hamiltonian, which is just sum over all positions. So this is the unit cell, if you like. These are labeled by integers, R. And okay, so there's this hopping and this hopping, if you like, and then we have the Hermitian conjugate. Just sum on R. And this A and T1 and T2 will be free to choose to be the same or different and so on. And we'll see that there are two different phases in this model. They're protected by symmetry, but depending on these the parameters we choose, T1 and T2, you can be in one or the other phase. And to go from one to the other, there'll have to be a phase transition. Okay, we'll see that phase transition is the closing of an energy gap for general values of T1 and T2. When you have one electron per unit cell, so one electron for every two of these sites, you'll have a band insulator. Okay, so there's an energy gap, but when you vary the parameters, that gap will have to close at some point and then reopen. Yeah.
I think the first atom in the Hamiltonian should be BR plus 1, right? Not a BR, right?
So these two sites are going to be both labeled by R.
Okay, I see.
Yeah. Yeah, you could pick some other way. You could label them differently.
Okay.
But I've used A and B for the two sites, and then I just need one coordinate for labeling. Okay, so we can solve this. So you want to solve for the spectrum. And you do that, of course, by Fourier transform. Okay, so let's say you have n sites and all, so you have periodic boundary conditions. Okay, all the usual things, and so then you can expand your modes in terms of these Fourier modes, okay, with some phase factor, which is so I'm going to keep this factor of length A, not to be confused with this A. A is kind of the distance between the unit cells, I guess. And there's some normalization to make sure they're all canonical operators. Okay, and as you know, this so that these things are periodic. So we have periodic boundary conditions. So there's no distinction between the label R and R plus L, R plus N, I guess. Sorry. Okay, so in order for that to be true, there's a condition on K. K times NA should be a multiple of 2 pi, okay, which quantizes this these crystal momenta K. Okay, so you can basically label them by integers. So if you solve that, put that back in the Hamiltonian, you can write the Hamiltonian as a sum over individual momenta. This Hamiltonian splits up, of course. It's a sum over these individual momenta. And each of those HKs is, actually, let me just write it as H. Yes, so there's some 2 by 2 matrix, which I'll call HK. And this HK is just, okay, so of course the diagonal terms are 0 because it only couples the A and B sites. So the terms that are on the diagonal are the AA and the BB coupling. Later, we're going to put in a chemical potential on each side, and that's going to give us a diagonal term. Okay, but right now there's no diagonal term. And we simply end up with I've taken T1 and T2 to be real here, just for simplicity. You can take them to be complex if you want. We just get the complex conjugates over here. Nothing changes, actually. Okay, so that's the Hamiltonian. And you can see that if I shift this K, okay, by integer multiple of 2 pi over A, okay, it just comes back to itself. Okay, it's periodic. And this defines for you a Brillouin zone. You don't have to label all the momenta. You only need to label momenta modulo 2 pi over A. That's just the Brillouin zone. So let me draw the spectrum now. So you have Ka ranging from pi to minus pi. It's the usual notation. And we'd like to write down the energy levels as a function of K, usual band structure, which is just the eigenvalues of this 2 by 2 matrix. Okay, if you're able to diagonalize this matrix, you'll just get a pair of eigenvalues, 2 energy levels for every K. Okay, and that's easy to diagonalize. It's traceless, so the eigenvalues are opposite, lambda and minus lambda. Their product is just the determinant. So you get that the eigenvalues at every K just that. Okay, and in general, you can show this has a gap. There is an energy gap between the lower band and the upper band. And there's actually, because of this particular Hamiltonian we have picked, there's a reflection symmetry of E to minus E. We'll talk more about that. That's going to be the chiral symmetry of this model. Okay, so let's analyze two limits, two very simple limits. Switch off either T1 or T2. So let's say T1 is okay, so really simple limits where in either case this dispersion becomes completely flat. Okay, this is the thing that gives you dispersion, cosine Ka. If either one of them are 0, this is gone. It's just a pair of two flat bands. Okay, so what does it look like in those limits? Well, in the limit T1 is non-zero. Only these two sites are connected, these pairs of sites are connected, and they're disconnected from one another. Okay, so the pair of sites will give you bonding and anti-bonding orbitals. They'll split. That's why you get these completely flat bands. So then you have an electron that lives on this pair somewhere here, basically, in the center. And this is sort of the picture of your band insulator. Okay, you have one electron for every two sites. It decides to pair the sides together like this. This is the A site. And put the electron in the center over there. Now, in the opposite limit, when T2 is non-zero, it's the other pair of sides that get paired, right? Okay, the electron is there. Okay, rather than here, again, it's a very simple insulator, but it's the other way around. Okay, and the important thing is that there's no way, given certain symmetries, there's no way to go from this configuration to that one without closing the energy gap. Okay, and that's the reason this model has a point where the gap will close, give you something that is metallic, actually it's Dirac-like, and then it'll reopen and reform itself into an insulator where the electrons are centered on the other set of bonds. Okay, so this is an extreme limit where the electron is literally sitting on this at this point. If you move away from this limit where one of them is 0, there'll be a spread of this wave function. Okay, it'll be exponentially localized, but it won't be it won't be this very tight kind of picture, but the center will be on this side or this one. Okay, this is a robust property. For example, if you had inversion symmetry, you could distinguish these two insulators in a sharp way. And it turns out also with this chiral symmetry, where this diagonal components are 0, sharp distinction between these two insulators. Okay, so ultimately the reason for a phase transition is very transparent physically from these pictures. We'd like to kind of see exactly how this spectrum closes and reopens in order to make this phase transition. Okay, so it's easy to show that if you were to monitor this gap, the place where it closes is when the two of them have the same magnitude. Okay, when T1 and T2 are the same. Okay, so you just look at that spectrum over there. Let's say T1 and T2 are the same. Okay, so you get a spectrum that looks at k equal to pi. It goes to it touches the other partner. Okay, and if you examine the dispersion right over here, okay, let me just blow up that part of the dispersion. Just linear. You just expand this cosine ka over 2 around pi over 2. Okay, we'll see, we'll do this a little more carefully. It's going to be linear in the deviation from this point Ka, and it'll have some Pauli matrix over here, and it'll simply be a Dirac dispersion. Okay, so it'll just be a one-dimensional Dirac fermion. Okay, and this is going to be a general feature that when you have a pair of phases, pair of topological phases, the phase transition between them very often is described by, at low energies, by a Dirac theory. Okay, so you can use this Dirac theory as a way, at least in that limit near this phase transition, near the boundary, you can use it as a way to look on either side. Okay, look on either phase and figure out if the two sides are really distinct or the same. If you had a system where there was a single phase, it would be unusual without fine-tuning to find such a band closing in between. Okay, so when you find that the band gap closes, there's some reason to distinguish the two phases. That's really the origin of this gaplessness, and you can use the Dirac theory to examine what that distinction is. Okay, so we'll see that either side, you can add a mass term to this Dirac theory. You can add a plus or a minus mass term that will open a gap, and the sign of having distinct phases is related to having a single such mass term. Okay, so when you have a Dirac theory, a gapless Dirac theory describing the phase transition, you can add a mass term to it to access the nearby phases. That will give you gap states, and when there's a single such mass term, that's a sign that there are topological phases. There's a phase distinction between the phases. You'll see in other cases there are two mass terms you can add. There are two things that you can add to this problem, which can introduce a gap. We'll see a second way of getting a gap is if you change the chemical potential on the sides. And once you do that, this distinction between phases will be lost. Okay, so really in this simple-minded picture, the classification of these topological phases reduces to counting how many mass terms you have. And those mass terms are going to be constrained by symmetries, for example. Okay, so let's do slightly better than the spectrum. Let's actually expand the Hamiltonian close to the point where you have these two being nearly equal. Okay, so And we're going to, later we're going to assume that this m is much smaller than t. Okay, so we can make some expansions and simplify this problem, sit near this, this gapless theory. Okay, so, so if you put that in, this hk. Okay, so I can expand this in Pauli matrices. Let me do that first. Okay, that's the expansion of this Hamiltonian in terms of Pauli matrices. There's just purely off diagonal. There's no tau z, but there's tau x and tau y. And now you put in this T1 and T2. That. Okay, and now we expand. Again, we just look near the Dirac point. Everywhere else it's going to be gapped. That's where the low energy physics is residing. So let's expand around this Ka. Okay, so the small deviation from pi is going to be called Pa. Okay, and then we get, let me call it Hp. C is actually T times A. Okay, so there's some kind of speed that appears times this momentum P. And then you have these Pauli matrices, and this is a constant M. Okay, so M is really the staggered part of this hopping. If the two hoppings are the same, this M is 0, you get this gapless linear dispersion. P is just linear in P. And there's an additional symmetry when you have these two hoppings the same. You can translate by what is otherwise a half unit. Right? If these hoppings were the same, there's no distinction. A and B sides, you can translate by a half hopping, by a half unit cell. And that in this Dirac theory turns out to correspond to chiral symmetry. Okay, it's like the right mover and the left mover will acquire a different phase factor. And that is what prohibits the gap. Okay, so there's a correspondence between, it's not an accident that this thing is gapless when the two hoppings are the same. Okay, so so now once you see this this kind of Dirac theory, you can sort of rationalize this phase diagram. So we said that if you were to okay, so we can draw a phase diagram with T1 and T2. Actually, let me just write it as T2 over T1. Okay, there's this point over here, 1, where you have a phase transition, okay, where the two are equal. And in this Dirac theory, the way you distinguish these two phases, on one side, when this T2 is smaller than the other one, this mass is less than 0. The other side is greater than 0. Okay, so this single mass term that you can add. And because of that, changing the sign of this one parameter, if you were to change some parameters, for example, the hoppings, you can influence the single parameter. You can change its sign. Single real parameter can change its sign. That gives you two phases, and they're connected by a phase transition. Okay, so okay, of course, what you'd really like is to have an invariant. You'd like to be able to calculate some topological invariant that will distinguish these two sides. We'll do that in a second. But at least from a low energy theory perspective, this is a nice way to think about it. You have a Dirac fermion, it's gapless, and you can change the sign of its mass. Okay, so now what happens if we add some perturbations to this? And of course, it's very important that you add the perturbations that break some relevant symmetries. Actually, let me quickly sort of describe what symmetries we have in this problem. The one I want to focus on, which is slightly unphysical symmetry, if you think about it as real electrons on a wire, but it's useful for our purposes, is what's known as chiral symmetry. And it's a little confusing because the word chirality is used in many different ways, but it means something very specific in this particular case. It means that there's a matrix, a fixed matrix. It doesn't vary in momentum, for example. Actually, that matrix is just going to be tau z. Okay, the tau z matrix distinguishes the A and B sides. Tau z plus 1 is A, tau z minus 1 is B. Okay, there's this fixed matrix that anti-commutes with the Hamiltonian. Okay, so tau z times h for any k is minus of, many different ways of writing it. So okay, so this guarantees for you that the energy spectrum is E to minus E symmetric. Okay, so if I have a state with energy E, I can act with the operator tau z. It'll give me a state with energy minus E. Okay, so this is going to be called, this is called chiral symmetry. And it's one of the symmetries that turns out to guarantee that you cannot add another master. Okay, so we said that this is the effective theory. And if you just stare at this theory, maybe there's another mass term you could add. Okay, so let's ask the following question. Okay, so to recall the way these mass terms work, these two operators anti-commute with one another. So when you look at the spectrum, you add the sum of their squares, right? That's how you diagonalize this Pauli Hamiltonian. You could actually add a third matrix that anti-commutes with the first two. So you could imagine you have this the kinetic term, but you also have a new mass term, tau z. Okay, and that exhausts all the Pauli matrices. But taken together, the spectrum of this will be the sum of the squares of all of them. There will be two mass terms now, okay, if you're allowed to add this new mass term. Okay, and if that is the case, you'll have to tune not one, but two things to 0 in order to cross the phase transition, or to cross the point where the energy gap will close. Okay, so now imagine you have this axis, there's this point right at the origin, but you have another dimension m prime. We'll come to what m prime is. It's really just a staggered potential, A and B having different potentials. Then you have to tune two parameters to hit the origin. Okay, that's not a phase transition. Okay, so if you want to go from here to there, you can avoid it by going around. Everything is in a single phase. Okay, so the distinction between these two phases is only present if you can argue why this mass term is not there. Okay, and so the symmetry you have to invoke to argue this mass term is not there could be different symmetries, but those symmetries will be required in order to have this phase distinction. Phases are distinct only if you assume a certain symmetry. Okay, so this is the idea of symmetry-protected topological phases. Okay, so for example, let's say you assume this chiral symmetry. You have this fixed operator, this matrix that anti-commutes with the Hamiltonian. Okay, so as long as you didn't have this mass term, certainly anti-commutes, tau z anti-commutes with x and y, but once you add it, it's no longer true. Okay, the Hamiltonian no longer anti-commutes with tau z. This will break chiral symmetry. So demanding chiral symmetry is one way. Is one way to exclude this mass term and thereby introduce a distinction between the two phases. Okay, so it will turn out that in the class, in the symmetry class with this chiral symmetry, turns out to be called A3. That's just the class of Hamiltonians which have this property. There's a fixed matrix that anti-commutes with them. In that class, it turns out that in one dimension, there is a Z classification of phases. Okay, you can label each phase by an integer. We haven't quite explained why it's an integer, but we see there are at least two distinct phases. Okay, so there's a distinction between them that requires a Dirac point to appear. Okay, so there are other symmetries that can protect this as well. Let me give you one other example, which is relevant for things we'll talk about later. It's the combination of reflection and time reversal. Okay, so mainly we will not talk about spatial symmetries, things that change the spatial coordinates, like reflection, but in this one case we will. We'll refer to this a couple of times. This is the one spatial symmetry we'll sometimes talk about. The thing that's nice about the symmetry is that the combination leaves K invariant. Okay, and you can implement it. And you can implement it by a combination of complex conjugation. And so the complex conjugation itself would change the sign of this term. For usual symmetry with time reversal, this is fine. This P would also change. But in this particular case, you want this to be restored. It would leave this invariant. So what you want to do is you want to multiply this with tau x. Okay, so this is your PT symmetry. And the momentum P goes to P. Okay, so this combination will keep these two terms invariant, but it will exclude this term. Okay, this will not be symmetric under this PT symmetry. Okay, so if we have PT symmetry, that's another way to exclude this term. Okay, so so maybe one word we should mention over here is about polarization. We talked a little bit about polarization. So it turns out in a system like this, which has inversion symmetry, you would think that the polarization is 0. Right? So if I told you a system has inversion symmetry, how can it have a polarization, a vector sitting there? The product of inversion and time reversal, well, time reversal doesn't do anything to polarization. Okay, so naively, this PT symmetric system would have 0 polarization. But it turns out in a crystalline insulator, polarization is only defined modulo 2 pi, right, or modulo this n times e. Okay, so it's actually possible to have a polarization of pi in the right units. You apply this symmetry, you get minus pi, but it differs from the original 1 by 2 pi, which is not an important distinction. So in fact, with this symmetry, you're allowed to have two values of the polarization, which is either 0 or pi. Okay, or if you eventually look at it in terms of Berry's phase, what you do is you compute the Berry's phase of these band structures, and you can either get a 0 or a pi in the Berry's phase. Okay, and that distinction ends up giving you a distinction between these phases, okay, at least with this symmetry. With inversion, you can have two kinds of polarization, simply correspond to the two sets of sites where the electron can live. It can either live in these centers, or it can live in those centers. Okay, and they're the two inversion symmetric places, but they're distinct from one another. Okay, once you introduce things that break this symmetry, introduce this kind of mass term, staggered potential, for example, the electrons can live elsewhere. You can have any value of the polarization, and this goes back to the problem we talked about, particle on a sphere, two-level system represented by a point on a sphere, and there the Berry's phase, as you go through the Brillouin zone, will give you the polarization. Okay, and you can get different values of the polarization. There's no constraint coming from the absence of this particular term. Okay, so so in the 1 minute I have left, let me talk about a topological way of distinguishing these phases when you're protected not by this PT symmetry but by this chiral symmetry. Okay, so so what is the topology of states in one dimension protected by chiral symmetry? Okay, so if we have this condition, the Hamiltonian should anticommute with this tau z. Okay, and if this is a 2 by 2 Hamiltonian, it basically means that it looks like that. Okay, in general, for a general dimensional matrix, you can have any matrix over here and its Hermitian conjugate there. Okay, this gives you a Hermitian matrix, and it anticommutes with tau z, represented in the same notation as, again, by 1, I mean it could be a matrix over here. Doesn't matter, it'll anticommute with this one. Okay, so that's most general chirally symmetric Hamiltonian. And again, we'll play this trick where we really don't want a dispersion of the band. We want to flatten the band dispersion. We want all states in the band to have the same energy eigenvalues plus or minus 1. Okay, and the way to do that is to choose this Q to be a unitary matrix. Okay, so if Q is a unitary matrix, if I take the square of the Hamiltonian, so if the Hamiltonian has eigenvalues only plus or minus 1, the square of the Hamiltonian should be the identity. Okay, all eigenvalues square to 1, simply the identity. So this is this flattening trick, equivalent to taking these unit vectors for the case of the Bery's phase. So for that, I just picked this matrix Q to be a unitary matrix. Okay, so if I square this Hamiltonian, you'll get Q dagger Q, which is just the identity. Okay, so the whole question of what are the distinct phases that can appear for these chirally symmetric Hamiltonians is reduced to a question of classifying these unitary matrices. So every point in your Brillouin zone, you have a single unitary matrix. Okay, let me just set up that thing and just tell you the answer for that. Okay, so you have Hamiltonian HK, which after some flattening, we said is just equivalent to some unitary matrix Q. Yes, we know how to go from one to the other. So the question reduces to classifying unitary matrices, or more specifically, you have a one-dimensional Brillouin zone. Okay, this is really just a circle. Okay, S1, if you like, it's labeled by this K, momentum K. You want to take maps from this to the space of unitary matrices. Okay, and you want to know what are the distinct, topologically distinct sets of maps. Okay, a very trivial map is to take every point and map it to the same unitary matrix. Okay, that's the identity operation. You can have others where you have not exactly the same matrix. You explore some space over here, but it's connected. You can shrink it back to one point. Okay, all of those are topologically equivalent to the identity map. But there may be others where you wind around. Okay, and to take the simplest unitary matrix, take a 1-by-1 unitary matrix, which is just a phase. Okay, so it's sometimes a little tricky to classify things with very small dimension n. In this particular case, it works. Did you have a question or no?
Oh, no.
Okay. So then what you're doing is you're mapping the circle S1 to a phase which is also a circle. Okay, maps from S1 to S1. Okay, yeah.
I think so too.
All right, okay. Next time, we'll continue. Yeah.